Hello everyone, I welcome you all on Data Phoenix webinar. Today we will speak about generate code using LLM, and with us Xinyun Chen. She is a research scientist at Google DeepMind, and she will share with us her expertise and her knowledge about generate code using LLM. So I give to her microphone.
Yeah, thanks for the introduction and also thanks again for inviting me. So can everyone hear my voice well and also see the stats well at this point? Yeah, okay, go ahead.
Yeah, I hear good.
Okay, cool. Yeah, let's get started. So I'm Xinyun. I'm a research scientist at Google DeepMind. So I've been mainly working on large language models for code generation and also reasoning in general. So in this talk, I will discuss my works primarily on large language models for code generation problems. So we have seen a lot of success for applications of large language models for code generation, especially for translating natural language descriptions to code. So here on the slide, I'm showing the basically one of the earliest large language models that have been shown very successful results on text code generation. So this is the OpenAI Codex model. So on the slides, we can see that with this large language model, the user just needs to describe their intended functionality in natural language, and also this instruction can be pretty detailed. It can include those concrete values representing the function arguments. So with this natural language description, then the large language model is able to generate the code to follow these instructions line by line. And basically, this code can be directly executable and give us the intended results. In many cases, the natural language alone might not be sufficient to fully describe the program functionality, especially the intended execution behavior. So to make the program description more concrete, we can also use other modality of the program description specification. So here on the slides, I'm showing another example of using input-output examples, which means that it also provides the intended program output when the input is with a specified input in the program description. So in the talk, I will also briefly discuss the AlphaCode work, which was also done at DeepMind. So in this project, we show that basically we can train a language model to perform at an average human program performance on those competitive programming tasks. However, with all this progress, there are still some fundamental challenges for those code generation problems. So the first challenge is that currently it is still very hard for the model to perform well in those algorithmic reasoning problems. So including the competitive programming problems that which we described before. So here I'm quoting a table from the GPT-4 technical report. So you can see that GPT-4 has been performing very well on several standard exams. This includes the SAT, GI exams. However, on this Codeforces rating, where Codeforces is an online competition platform for those hard coding problems, we can see that if we do not have some good design for the inference time, and if we just naively use GPT-4 to decode results, then basically this rating is among below 5% of all the human programmers. So actually, this concrete rating just means that in several online competitions, basically the GPT-4 model can nearly solve non-problems in any context, even for those simplest problems. The second challenge is that even for those simple coding problems, the large language models might still fail to solve them. And this is especially true for those problems which are specified with input-output examples. So on the slides, we are showing another failure case of GPT-4 model, where basically the problem description includes both a natural language description saying that we want the function to give a loss amount if the given amount has a loss, else return none. So this description basically means that we want to compare two arguments for the function. If the first argument is greater than the second one, then we want the model to return none. Otherwise, we return the difference. So this is basically what is described in the following assertion statements. So if we look at the generated code, we can see that this code is largely accurate, except that it basically wrongly swapped the order of the two given arguments. So this basically shows some weakness of the large language model in understanding the code execution, and it can basically fail those simplest assertion statements. So basically, given these challenges, in this talk, I will discuss 2 lines of my work. Firstly, I will briefly discuss some techniques in our AlphaCode work for showing that large language models can solve computation-level code generation by leveraging the code execution for code re-ranking. Now, secondly, I will discuss our recent work, Self-Debugging, where we show that we can teach large language models to debug their own predicted code, like how human programmers do debugging. In this project, we will show how we can leverage the execution to improve the sample efficiency. So let's get started with the first part about large language models for solving challenging algorithmic reasoning problems. So first, let's do a recap of our competitive programming problem format. So basically, the program format includes 2 parts. The first part is a natural language description, and the second part includes usually a few pairs of input-output examples specifying the program execution behavior. But different from many standard coding tasks, for competitive programming, because the problem is basically described in a way to confuse even the best human programmers. So you can see that actually here the problem description is pretty long and complicated. It usually includes a lot of background story that is not directly mapping to the actual code we want. And also, basically, this text description doesn't really detail the concrete algorithm we want to implement. It is more about describing the execution behavior at a higher level. And for the programmers or the large language models, they need to figure out the algorithm themselves. And also, in many cases, it also needs to optimize the actual implementation so that it can pass all the input-output examples. Then, given the problem description, the goal is to generate the corresponding code. So here on the slides, I'm showing an example of the code which is correctly generated by the AlphaCode model. We can see that this code is definitely non-trivial. It includes those loops, conditions, etc. And in particular, the main challenge here is that there's no direct mapping between the given problem description and the output code. So basically, in this implementation, the model also needs to come up with the most optimal algorithm to solve such problems. So to summarize here for the challenge, the first thing is that the model needs to not only understand the natural language itself, but also need to come up with an efficient implementation. And the main reason is because the given input examples in the problem description usually are just a few simplest illustrated examples. And the predicted code also needs to pass many more hidden test cases. And these hidden test cases are often more complicated and larger scale. So it basically requires the model to generalize this solution to broader use cases so that it does not overfit just to the given input examples. And finally, from the large language model perspective, one important challenge for solving competitive programming problems is generalization. Because in many cases, for those standard coding practices, the new code might not be just written from scratch. There might be some reusable library course which can be directly adopted from existing programs. But for those coding contexts, the new competition level coding problems are usually very different from the previous problems on a surface level. So this is why, for example, for the GPT-4 model, its generalization performance can be pretty poor when solving those new coding contexts because they can look very different syntactically from all the previous coding problems. Then given this challenging task, what we can achieve now? So basically here I'm showing our AlphaCode results where we evaluate our models on the Codeforces platform. We ask the model to participate in 10 contests where there are over 5,000 other human programmers per contest. So our final model is an ensemble of 41 billion and 9 billion models. And for each problem, we allow the model to give like 2 attempts, to give 10 attempts. And basically these 10 attempts are like collected from the solutions from both models in the ensemble. So here on this like plots, we are showing the average ranking of this like of our model in this like 10 contests. So basically, if we consider all the ratings, then our model can perform among like around top of 54% among all the human programmers in each contest. And if you consider this rating for all the Codeforces users, actually it is among top 28%. So this result is clearly does not match those very top human programmers, but here we can see that it is still a good milestone to show that our model is able to solve some new coding problems with non-trivial performance. So given these results, one natural question is whether further scaling up the model can just allow the model to solve more models, for solving more problems. Because like for example, in the earliest like OpenAI GPT-3 models, we know that the model size is around like 175 billion parameters. And also for the the earliest Google PaLM model, the size is around 540 billion parameters. So to answer this question, here I'm also showing this scaling curve by comparing performance of models with different sizes. So if we compare different curves, especially by comparing the red and purple curves representing the 9 billion and 41 billion models, we can see that actually this performance gain becomes less and less significant when we are using a larger model. In particular, if we focus this data point, we will only allow each model to decode 10 like solutions. Then we can see that actually no model can achieve a decent performance with such a few samples. So basically, this indicates one thing inside our like overall pipeline. So earlier when we talk about sending 10 final submissions per problem, actually that does not mean that the model only decodes 10 submissions. It means that actually these 10 final solutions are coming from much more initial samples for the model to select from. And in practice, actually to achieve the best results, we allow the model to decode 1 million programmers per problem. Then we propose some selection techniques to basically pick up the 10 final submissions. So here I'm showing this overview of the AlphaCode pipeline. So this pipeline includes the standard learning and inference stages. So in the training stage, we have this pre-training pipeline by training the model from GitHub code. Then we have this fine-tuning stage where basically we collect our own dataset called code contest, which includes previous competitive programming problems with their solutions. Now after the training stage, at inference time, we perform this large-scale sampling by basically decoding 1 million programmers per problems. Then given this like very large set of like candidate solutions, then we have a ranking stage where we allow the model to basically select 10 final submissions for the full evaluation. So in this talk, I will primarily focus on this stage of filtering and clustering for selecting the final solution, which is actually crucial for achieving a decent performance on these very challenging coding tasks. So the high level idea, the core idea for this process is to leverage program execution. So let's first talk about this filtering stage. So basically, the idea is that we will execute all these generated programs on the sample tests provided in the program description. Then we filter out those programs that do not even pass the given tests. So note that earlier we mentioned that for each task, it includes both example tests and also hidden tests. So basically, after this filtering stage, even if the code passes the given example test, it does not mean that the solution is necessarily accurate. However, even if there are only 1 to 2 simplest tests in the problem description, still we can see that for all these models with different sizes, over 99% of the programs actually cannot even pass the sample test. So on the other hand, this also shows the weakness of the model's understanding of code execution, as we mentioned before. So after this filtering stage, assuming that we have 1 million candidate programs, then basically remaining 1% programs means we still have 1,000 programs to select from. So basically for the clustering procedure, we will further utilize execution to select from the remaining programs. So recall that the main challenge here is that for those test programs, the hidden tests are not available. But at least for the training programs, because we have the ground truth programs, so this basically allows us to generate as many test cases as we want for training programs. Then basically we can train another separate model only for generating new test inputs. Then with this model, we can then also generate these new inputs for the new test programs. Then we execute all the sampled programs on these generated inputs. So assuming that I can allow the model to generate many inputs, such as on a scale of 100 to 200, then we can basically cluster all those programs with the same outputs together. Here we assume that if we have enough generated inputs, then for those programs that can provide exactly the same execution results on these inputs, we can assume that they are semantically equivalent. Then after this clustering, we can then such as sample one program per each of the 10 largest clusters. The intuition here is that basically for those wrong predictions, they can be wrong in many different ways. But for those correct solutions, they might be more they might tend to be more centralized together. So basically here we are following the consensus for the large language model samples. So with that, here we are showing the effect of this filtering and clustering procedure. So we can see that by comparing the red curve to other curves, this filtering procedure is crucial because, as we mentioned before, over 99% of the programs cannot even pass the sample test. So basically, by filtering this larger number of samples, we can allow the model to have higher chance to select from those correct ones. Then if we compare those results in the bottom table, which shows the improvement by scaling up from 9 billion to 41 billion, as well as scaling up from 41 billion to the version with clustering. We can see that clustering with generated inputs can even provide more performance gain than scaling other models. So this again shows the importance of leveraging code execution. However, if we compare this performance with the blue curve, which is the Oracle results, so this Oracle result means that we assume the model can just submit, let's say, all the 10 million programmers for the final evaluation. So basically, this shows the highest performance we can achieve with the current trained model. So if we compare this Oracle solution with those other versions we evaluated, we can see that there is still a gap from the Oracle sample selection. So this also demonstrates that we still need to improve our approach to really differentiate those high quality solutions from the lower quality ones. So basically, from the first part, we show that we can, if we can scale up the language models, basically, and also to properly train the model for solving those coding contests, then this scaling can enable the model to really go beyond memorization and solve unseen challenging algorithmic reasoning problems. And also, in this part, we show that leveraging the execution results can really improve the complexity of synthesized programs by utilizing the input-output examples. So this basically further shows that sampling at the inference stage can really allow the model to achieve something qualitatively different. However, definitely we can still see a huge gap to top human programmers. So for the long-term challenge, still we want to improve the model's its own coding capability so that it can in general come up with those correct solutions more frequently. So then in the second part, I will discuss another work which is called self-debugging with large language models. So recall that at the beginning, we discussed that this large language model generated code in the first round can be problematic. And also these issues can happen even for those simpler coding problems, not at the competition level. And this is mainly due to the weakness for the model to understand those input-output specification and also those assertion statements. So for the AlphaCode approach, we demonstrate that we leverage this code selection by using execution results, and also this is done with the large-scale sampling. However, we can clearly see that with this code re-ranking and sampling strategy, the sample efficiency is kind of suboptimal because firstly, it requires a lot of model samples to select from. And more importantly, the fundamental weakness here is that this sampling, re-ranking, and selection procedure does not really utilize those wrong predictions to improve the code quality in the second round. Because all these massive number of samples are just generated independently. So this means that the same wrong code can be just sampled many times. So in this way, a lot of samples are just wasted to repeat the same mistakes. On the other hand, if we think about us as human programmers, actually, human written code in the first trial is usually also not perfect. So this is why debugging is such an important skill for human programmers and includes those very top human programmers. And actually, somehow this debugging skill is also a good differentiator to really distinguish between good and also weaker programmers, because those good programmers are able to identify bugs by themselves, and this is usually done by investigating the execution results and also think deeply about the underlying code semantic meaning. So basically, in this self-debugging project, we follow this intuition of human debugging process, and we want to teach the large language models to do the same by debugging their own code. And this pipeline is motivated from the RoboDuck debugging process. So basically, RoboDuck debugging means that for human programmers, when we are getting stuck with some unknown issues in the code implementation, so we might not necessarily need to ask for another person to give us guidance. Instead, we can basically put a RoboDuck or something that cannot give us any feedback on that. And then basically with this RoboDuck, we can explain our code in natural language line by line. Then in this process, even if there is no external feedback from anything else, but with this explanation process, in many cases, we will suddenly realize those inconsistency between the code implementation and actually the actual functionality we want. So basically, by this this RoboDuck debugging process, it can basically help the human programmers to really dig into those implementation details and find those starter bugs. So with that high-level intuition, now I want to basically explain the overall workflow of the self-debugging process. So in each debugging step, basically the model will first generate some new code based on the problem description, and also we can utilize unit tests when applicable. Then in the second step, we will execute the code and then basically collect the execution results. So these execution results can be those actual outputs for the given program input, or it can also be some runtime error messages. Then in the third step, we then basically instruct the large language model to explain the generated code line by line, and this explanation will be in natural language. With the execution results and also the code explanation, Then the model will generate a feedback message itself, saying that whether the large language model thinks the current prediction is correct or not. If the model thinks the prediction is correct, then basically this debugging process will terminate, and the model will just return the code generated in the final run. Otherwise, basically the model will include all those like generative feedback messages, as well as previous predictions, execution results, and all this like information will be appended to the previous like model input. Then all these results will be utilized for the next round of debugging. So this debugging process will terminate when the model like comes with a right solution by its own, or we can also like basically say that the prediction process fails if the model just cannot improve its own performance after many tries. So here I want to show a simple demo with the Google bot model. So in the first stage, basically we ask the model to generate the code. And basically this is the same failure case we showed before for GPT-4. And also here the bot model make the same mistake by like wrongly swap the order of the two arguments. Then with this prediction, we basically here we show that we execute the code and provide the execution result as the feedback to the model. Basically here we say that we demonstrate what is the actual output given the current predicted code, and what is the corresponding assertion statement. And here by comparing these two, we show that the code does not pass the assertion. Then we ask the model to fix the predicted code. So with this like feedback of the execution results, then the model can quickly realize that there is this like a mistake in its if condition. Then the model correctly basically fixes the bug here. So if we do not give this like feedback and just ask the model to sample multiple times, the model might still come up with a correct solution at some point, but in many cases it will require much more samples to reach to the correct solution. So now I want to like provide some other like applications where there's this self-debugging can improve performance. So the first task is the text-to-SQL generation. So basically for text-to-SQL generation, the model input includes this natural language question. Here the question is which customers have both on-road and shipped as order status. List the customer names. So this is a question where the required SQL query will return a table with one column. And also here we can see that there's the where condition where we try to basically ask the model to return a table which is an intersection of two conditions. Then for text-to-SQL generation, one challenge is that we want the model to achieve cross-domain generalization. This means that each question can ask about different databases. This is why actually in a problem description, it also includes the database schema. So in general, this makes the specification of SQL prediction in many cases much longer than the other like standard coding programs with an executable standalone function. Another challenge is that for text-to-SQL generation, in many cases, it does not have unit tests. So this means that the model needs to infer the code correctness by itself. Because here we do not know the intended execution results for this in this program specification. So given this problem, our approach here is to perform self-debugging by explaining the potential inconsistency between the generated code and the question. So here, let me show a concrete example. So for the first step, we will ask the model to explain both the question and the generated code. So for question explanation, the most important goal is to ask the model to do some kind of type inference. So here with this question explanation, it will basically do a make a hypothesis about the intended return a table format for the given question. So for example, here the model predicts that the question should return one column of a table. Then the second step is called co-explanation. So here basically the model will explain the generative SQL query. So here we can see that basically the model generative explanation is a clause-by-clause natural language description about what each part of the SQL query it means. So this includes explanation of the select clause, the where condition, and also the list join statement. So if we take a closer look at this question and the SQL query, we can see that actually this predicted SQL query is wrong, because in the initial question, the condition should be the intersection of both on row and shift. But in the predicted SQL query, the keyword here is all. So you can see that actually there's an inconsistency here. Then by showing this explanation of both question and code, we can see that then the model generates this feedback message saying that the prediction is wrong, please fix it. Then with this feedback message, then the model do a round of revision. So here we can see that it changed this keyword all into and, but still this is a wrong SQL query, because here basically it assigns the same the different values to the same column. So this means that the where condition, the where clause contains these mutually exclusive conditions. So this means that this SQL query will always return empty, which is not all we want. So with this explanation, then the model again says that the prediction is wrong, please fix it. Then in the second round of revision, the model correctly predicts this intersect keyword to basically connect the two conditions. And this time the model will return a feedback message saying that the prediction is correct. So the highlight for this self-debugging process is that basically here, this process does not have any training process. So basically we just leverage those pre-trained large language models for code out of the box. And for all these steps, except for the execution results, which are provided with this intersection with an executor, then for all the other information, including the generated code, the explanation, and also the feedback message, these are purely came out from the model itself. So basically in this debugging process, there's no human in the loop. So all the feedback, only external feedback is the automatic execution results, which also does not require humans to do any additional explanation or annotations. Then the second application is code translation. We want to translate the code from one programming language into another. So for slides, I'm showing this example of translating from C++ to Python. So because in the code translation application, we already have the reference code, which provides this information on the intended execution behavior. So here we assume that all the unit tests are available for debugging. So for code translation, the large language model itself does not need to infer the code correctness. So it can focus on how to fix the wrong code. With this unit test, it allows us to explore more feedback formats for self-debugging. So simply, feedback is basically a short universal message for all the correct or wrong code. So for all the correct code, it will say that the predicted code is correct. But for those wrong code, basically we only provide a feedback message saying that the code is wrong without giving any program's case specific information about what the code is wrong about, and also what is the other additional information. Now for the unit test feedback, besides this conclusion of whether the code is correct or not, it also includes the execution results. So here the execution results can be the actual program output, and also how it compares to the assertion statement, and as well as those runtime error messages. This can also be provided as part of the unit test feedback. Then for the code explanation, again, it will be a line-by-line explanation of the implemented code. So the slides will show this explanation for both C++ and Python. So basically, here it is an interleave of the original program statement and their natural language description.
And finally, here we also incorporate another feedback format called trace. So basically, this is still an explanation of the generated code line by line. But basically, here we also ask the model to explain the execution results after each statement. So here I want to note that the execution trace is not the actual results from the executor, because in practice we know that there are a lot of programming languages where this kind of partial program execution results are not that applicable to obtain. So basically, this trace actually is fully predicted by the model. This means that the execution trace itself usually can contain errors, especially at the intermediate statements. But interestingly, we can see that even if the trace feedback itself is not that precise, still, in many cases, this trace can provide some more information, and especially to reveal the understanding of code by the language model itself. And this information can still be helpful for the model to perform debugging. So here on the slides, I'm showing the overview of how these self-debugging turns look like. So basically, at the beginning, we have these general instructions telling the model that we are going to do the debugging process. And for those procedures that include more information, like here for explanation, we have some other instructions saying that we ask the model to do explanation line by line, or ask it to trace the execution. Now with this initial instruction, then the model basically provide to perform this debugging process turn by turn by generating the code, explain it, and then take the feedback message to do the future revision. Then the third application is text to Python generation. So here we utilize this MBPP benchmark, which is a standard benchmark for many coding large language model projects. So basically here, our setup is that we will have one unit test in the prompt. And also we have other hidden unit tests for full evaluation. So as we mentioned in the AlphaCode part, this setup basically means that passing the given unit test does not necessarily lead to the final correctness of the predicted code. So basically, in this case, the model still needs to infer the code correctness when the predicted code passes the given unit test. But still, because we have at least one unit test in the problem description, we can still utilize this unit test to give us a lot of information about the code correctness. So, for example, if the predicted code even cannot pass the given unit test, it means that the code is definitely wrong, so we need to fix it. So now I want to show the overall results of the self-debugging process for all the different benchmarks. So here we evaluate multiple models. This includes the OpenAI Codex model and also GPT 3.5 and GPT-4. And also we compare with this StarCoder model. So StarCoder model is a 15.5 billion open source coding large language model. So we can see that if we compare the baseline results of all models, which means that we just ask the model to decode the program without any debugging, then the baseline performance varies depending on the underlying coding capability of the model. But for all these different models, self-debugging can consistently improve the performance. And in particular, if you allow the model to utilize the unit tests, for example, for the transcoder and MBPP benchmarks, then this improvement can be pretty huge. It can be around 10% for different models. Now to dig into more details into these results and compare the results for different models and also for different setup, different feedback formats. So in general, we can see that more informative feedback can improve the self-debugging performance. But here I want to first note that because for transcoder and MBPP, we utilize the unit test execution to basically to indicate the code correctness. This is happens to both the simple feedback and also for other feedback that actually contain execution results as part of the model input for debugging. So this utilization of execution is the reason why simple feedback still can improve the performance. Because even if you just tell the model that the current prediction is wrong without giving any extra feedback, still it allows the model another chance to provide us with a different solution. So basically, this process still allow the model to overall improve its prediction quality. And later on, I will show another application where we do not have the execution results as a feedback. So in that case, basically this simple feedback nearly cannot improve performance at all. Then in particular, we can see that adding execution results is very important. It consistently improves the performance over the generic simple feedback across different models. And finally, if we utilize this large language model generated code explanation, it can provide additional performance gain, especially for those stronger models, which can take advantage of a richer feedback information. Next, I want to show this the performance for a spider benchmark, which is for text to SQL generation, and also compare the performance to MBPP, which is text to Python generation. So first, I want to note that for the one core difference between the OpenAI Codex model and also the later GPT 3.5, GPT-4 is that Codex model is not conducted with instruction tuning, which means that if we utilize this Codex model, we cannot do our prediction task with zero-shot prompting. We need to give it a few exemplars to demonstrate what's the task we want to perform and also what's the prediction format. So by comparing these different models, we can see that actually Codex performs the best at SQL with SQL than other models. Also for the Python task, we can see that later generation of the GPT models consistently improve over the previous results, especially for the baseline results. So the main reason here is that we can hypothesize that the GPT model is not optimized for SQL query, because the SQL is not that popular compared to other languages like Python. And also in general, after instruction tuning, GPT 3.5 and GPT-4 is less capable of following the future prompting format. On the other hand, Codex can follow the format better. So basically, we can see that on this task where the model is not optimized for zero-shot prompting, Codex has the potential to perform better than the other models. And if we consider the performance gain achieved by self-debugging, we can see that actually the performance gain with GPT-4 is on par with a Codex. So they are both around 8 to 9%. Now I want to show some other discussion breakdown to demonstrate the some advantages of self-debugging. So first, we want to discuss about this sample efficiency aspect. Here we are comparing the baseline prediction performance with the version with self-debugging using different number of samples. So if we compare the results achieved by self-debugging from gradient decoding, which is around 80.8%, with the baseline results using 16 samples, which is 80.7%, we can see that actually self-debugging from gradient decoding kind of match the baseline performance with utilizing more than 10 times samples. So this basically shows the improvement of sample efficiency. In particular, if we only use the baseline approach without using any feedback, then at a certain stage, the prediction performance converges. On the other hand, with self-debugging, we can basically achieve additional performance gain with more samples. Then the second question is what is also discussed, what kind of errors can be fixed by self-debugging? So earlier we demonstrated that for text to SQL generation, the overall performance improvement is around 3% using the Codex model. And here we are showing this breakdown of the prediction results from different difficulty levels. So here, this difficulty level of the prediction task is decided according to the complexity of the ground truth SQL query. So we can see that actually self-debugging improves performance mostly for those harder problems. And in particular, on the extra hard SQL task, the improvement is 9%. So when we look at what kind of errors are fixed by self-debugging, we can see that self-debugging mostly fixes those startup mistakes. For example, missing wheel conditions or missing select columns, or basically predicting extra select or wheel conditions, select columns and wheel conditions. So these kind of issues happen more for those more complicated SQL queries. So this is why self-debugging can improve more on solving these harder SQL tasks. Because if we just ask the model to decode samples, it usually will just make mistakes here and there. And I also want to note that in general, self-debugging does not improve the fundamental coding capability, since there's we only perform this prompting procedure without fine-tuning the model. As a result, if the mistakes made by the model is primarily because the model come up with the wrong algorithm, or the model cannot even understand the problem itself, then self-debugging itself does not solve such problems. So this is why after self-debugging, we can still see that the final performance varies across different models. So this actually follows the intuition of human debugging, because for humans, the debugging process is also mainly about fixing those implementation in a code, especially to basically find out those small mistakes that cause all the overall errors during execution. So if for human programmers we are having trouble about coming up with the right algorithm, then this is usually not the job of debugging. This is the job of further thinking about the question and to really come up with the right algorithm. So earlier we mentioned that code execution can really give us a lot of performance improvement for self-debugging. So here I want to further demonstrate the importance of code execution by discussing this application of self-debugging results without using code execution. So here you can see that if we do not allow the model to execute the code, which means that all these feedback messages, including the correctness of code, is fully inferred by the model, then in this case, the self-debugging performance is definitely less significant. But still, we can see that overall, this process can still bring up to 5% performance gain with the Codex model and GPT-4 model, especially for text-to-Python generation. And when we are not allowed to use execution to help the model to self-debugging, we can see that in this case, actually, the execution trace feedback can really improve performance with a non-trivial gain. So since this trace feedback actually is trying to simulate the execution outcome. So here we can see that even if the trace feedback in many cases might not be precise, not all the intermediate execution state is correct, still it provides helpful information for the model to better understand the execution process and also to perform the debugging. So here I want to also extend the discussion to other problems in general. So basically here we also want to discuss in general for large language model self-correction for reasoning tasks. So basically here for the comparison, we include two results. The first result is the version with Oracle, which means that we utilize the ground truth answer in the correction process. So basically, for each reasoning task, like GSMAK for solving math problems, and also common sense QA and hot pot QA for text reasoning. So basically, the Oracle version means that we will first tell the model about the correctness of the solution, utilize the ground truth answer. Then basically, the model will correct its own prediction only if the prediction is wrong. So with this version, we can see that basically, if we ask the model to generate another solution, this overall performance can be better because it never changes the correct solution into wrong ones. However, if we do not use Oracle feedback for correction, which means that the model needs to judge the correctness of the prediction by itself, then in this case, actually, these large language models can wrongly change those correct solutions into wrong ones. So overall, actually, this process will lead to worse performance. So basically here, this shows some differences between the code reasoning tasks to the other like text reasoning or math reasoning tasks. Before code generation, actually code execution provides a very natural, valid external feedback. Since humans also often debug with the IDE, with this like seamless intersection with the interaction with the overall execution environment. On the other hand, for solving like reasoning problems, especially in the like test setting, it is not that natural to actually assume that we have access to the autocode results already. So basically, to summarize, in the second part, we show that we can teach the large language models to do self-debugging with fusion prompting. So this can be done even for those models that are not specially tuned for debugging. So this includes OpenAI Codex and also for the open source star coder models. We can see significant improvement across like several coding tasks with self-debugging, including those problems that do not have unit tests, like text-to-SQL generation. Another note here is that actually for self-debugging, we do not just want to propose it as an approach to like improve the empirical results. We also propose it as one indicator of the large language model coding capability. So in the future, even with like stronger and stronger coding large language models, still in many cases, the model might not come up with the right solution in the first trial, same as human programmers. However, if we can show that the large language model can just improve its own prediction by taking those like available external feedback, then we can still argue that for those models that can correct its own mistakes more frequently, this can be like stronger coding large language models, and they can also be more reliable. So to summarize the both works in this talk, basically here we show that large language models can provide as a unified natural language interface for general purpose code generation problems. And also like language models show promising progress on solving unseen challenging coding problems, but definitely with room for improvement for those like more complicated problems. We want to improve the sample efficiency so that the model can come up with high quality solutions more quickly. And also like self-debugging enables the large language model to leverage code execution and reflect on the code semantic meaning to fix its own prediction, which overall also can improve on the sample efficiency by taking additional feedback to correct its to basically find the correct solution quicker. So this is the end of my presentation. Thanks a lot for listening. And now I think we can open up the Q&A session and also to take questions. Thank you.
Yes, thank you for this very interesting presentation. We have several questions. Let's answer for them, and maybe we can continue in our Slack channel to discuss more. So first question about, do I understand correctly? Sorry. Yeah. Do I understand correctly that AlphaCode assume to understand what the code should be do by looking at input-output as a specification?
Yeah. So basically, for the AlphaCode problem, so yeah, basically the problem description includes like two parts. One part is like natural language question. And also another part is like input-output examples. So basically, the model can take both information to propose the program solutions.
Okay. Can you explain, like IM5, how do you run back prop on execution result?
Yeah, thanks for the question. So actually, if we think about the training procedure of these like language models, like for the AlphaCode process, so actually, this back propagation is so this is why actually in the fine-tuning data, it is actually still a supervised data. So basically, I think we have this like a process here. So when we are training the model, first for the pre-training step with the GitHub code, it is the next token prediction task. We just ask the model to basically reproduce those like tokens in the GitHub data in an auto-regressive way. Then for the fine-tuning procedure, basically we assume that in our data set we have the problem descriptions of the coding context tasks with their actually ground truth solutions. So with the ground truth solution, again, when we are training the model, the back propagation is about asking the model to just reproduce these solutions for the given coding task. So this execution part is not like differentiable. So we are not doing this back propagation based on the code execution task. But definitely for example, for future models, if you want to ask the model to better understand the code execution, then we might design some process so that the model can actually learn from the execution results as well. Yes, thanks for the question.
And one question. When self-debugging, how do you do incremental regression? Just start from same speed or something else?
So basically, for this like debugging process, so the first step is just about generating initial code. But let's say if after one turn of debugging, the model still thinks the prediction is wrong and it needs to continue. So basically, for the previous turn of like the feedback, including the previously generated code, the execution results, and also the explanation of the code, all this like information will be concatenated with the previous like problem description. So at least like a longer input context, including the like debugging trajectory, will be taken to as the model input for the next round of debugging. So this is how the input is changing per each debugging turn.
Okay, thank you for this presentation again, for answer for questions. About question about presentation, yeah, we will publish the video and I hope the presentation as well. So you can find all this information on our website. And thanks again for all who was with us, and Xinyun, correct?
Yeah,
yeah, it's a little hard to pronounce your name, but I hope I will do it correctly. Thank you again for this cool presentation, and for all, see you on the next webinar.
Yeah, thanks. Yeah, thanks again for everyone to attend the talk, and also thanks again for inviting me to present at this seminar.
Yeah, thank you. Bye.
Yeah, thank you. Bye.